Problem 3.59. In this problem, we have water flowing through a pipe contraction shown in the figure below. For the given 0.2 meter difference in the manometer level, we need to determine the flow rate as a function of the smaller diameter, d. Okay, so the first thing that we're going to do is we're going to create a table of the information provided at each point. And so we could figure out what is the next steps that we're going to do. Okay, so we have pressure, we have velocity, we have elevation, and then we have areas. Okay, the pressures at 0.1 and 0.2 are not known, so we just don't know those values yet. The velocity at 0.1 is a static point, so the velocity we do not know. And we label this point as 1, this label as 2. And the 0.2, because it's going into this tube, it has a dynamic pressure, so the velocity will become 0, so it's a stagnation point, so the velocity will be 0. What we know about C1 and about C2 is that the values are going to be the same. There is no difference between the elevation, so we're simply going to write that they are the same. The radius the area that we're going to have in each one of the cases, in this case is going to be pi d squared over 4. And for the time being, I'm going to label this small d. So it's pi d squared over 4. So then we'll substitute the values. Okay, so we're going to start by writing Bernoulli's equation between these 2 points. So P1 plus 1/2 rho V1 squared plus gamma Z1 is equal to P2 plus 1/2 rho V2 squared plus gamma Z2. And then we're going to cancel the values that we have here to be 0. In this case, the velocity at 0.2 is 0. And the elevations are the same, so they cancel out. Okay. At the end, what this tells us is that the pressure at 0.2 is simply P1 plus 1/2 rho V1 squared. Okay, so we get this relationship between pressure differences based on the Bernoulli's equation. We cannot apply continuity because one of the 2 points in question has a velocity of 0. So the only thing that we could do is evaluate hydrostatic pressure. So we're going to call this point 0. So P2 is going to be P0 plus this distance from here to here. And if you see, this distance is 0.2. We have an elevation over here. We're going to call it H. So it's going to be gamma of water, 0.2 that we have, plus H. So that's on the pressure 2. Pressure 1 on the other side is going to be also, this is P0, atmospheric pressure, P0, plus gamma. And then from here to here, if you notice that dimension is equal to the same H that we substituted back there. So this is H. We're going to take these 2 values of pressure and we're going to substitute them in the original equation. So P1 is going to be P0 plus gamma H plus 1/2 rho V1 squared. And P2 is P0 plus gamma times 0.2 plus gamma H. And as always, the values of H, the values that are not included in the head, they have to cancel out. Also the value of P0, because it's also 0, cancels out. So at the end, what we get is that 1/2 rho V1 squared is equal to rho times G times 0.2 meters. Okay, so from here, notice that the density cancels out, and we're able to find the value of the velocity. We solve for the velocity. V1 is going to be equal to 2 times G times 0.2 meters. And then the square root of this. And then the value of this is going to give us 1.98 meters per second. Now that we have the value of the velocity, we could calculate the value of the volume flow rate. So Q is equal to either A1 V1, and that is the velocity that we have over here. And in that case, we have pi d, which is 0.1 meters squared divided by 4. So that's the area at 1. And we multiply it by the area, by the velocity, 1.98 meters per second. And if we multiply this out, we find that this is equal to 0.0156 meter cubed per second.